Hello, everyone. My name is Paula Scotti, and as president of the American Astronomical Society, I'm very happy to welcome you to our Henry Norris Russell lecture by Dr. Scott Tremaine. I'm really happy to do this because we usually present our award at our January meeting of the AAS, and I was living at an island away from Seattle at that time due to the pandemic, and 1 hour before Scott's lecture, the power went out to the entire island for the day. So I missed his entire talk, and Michael Strauss stepped in at the last minute to do the introduction. So I'm really happy to be able to have the chance to have a do-over. The Henry Norris Russell Lectureship is our highest award in the AAS. It's chosen annually on the basis of a lifetime of eminence in astronomical research. And the tradition between the RAS and the AAS in the last few years is that we exchange the lectures between the two groups. So we're very happy that Scott can give his lecture to yours. And we had Sandy Faber give the 2020 gold medal lecture at our AAS meeting as well. So here is the copy of the citation. We have a certificate as the award for the Henry Norris Russell Award. The citation reads, it's probably too small for you to see the fine print, so I'll read it to you. For his lifelong contributions to our understanding of the dynamics of natural cosmic systems on scales ranging from comets to clusters of galaxies, and for his mentoring of junior colleagues in leadership of major astronomical research institutions. Scott is a Canadian by birth. He's bounced back and forth between Canada and the US throughout his career. He received his bachelor's at McMaster University in Ontario, Canada, his PhD at Princeton in the US. He had postdocs then at Caltech and Cambridge, England, and then became an associate professor at MIT in the early 80s. In the mid-80s, became the first director of the Canadian Institute for Theoretical Astrophysics, CITA, in Toronto. And then in 97, he moved over to Princeton, came back to the US, was chair of the astrophysical science departments from 98 to 2006. And then since 2007 on, he's been at the Institute for Advanced Study in Princeton. Scott has many, many science accomplishments. He really does the dynamics of the universe. His notable accomplishments include how shepherd moons interact with the rings of planets, especially for Saturn and Uranus. He's worked on short period comets and determined that they come from the Kuiper Belt and helped coin the term Kuiper Belt. He works on the dynamics of galaxy centers, perhaps the most well-known one of Andromeda, the double nucleus, and he's an expert on planet formation. Basically, every single graduate student in the US uses his textbook on galactic dynamics. I don't know if that's true in the UK, but you know, it's the classic textbook, Binney and Tremaine. First edition was 1987, and it still is used today. So it just attests to how wonderful that book is. And Scott has won a number of notable awards. I don't have time to list them all. He's won basically every award that the AAS has, the Warner Early Career Prize, the Heinemann Mid-Career Prize, the Brower Prize from the Dynamic Division, the Russell recently, and he became a Legacy Fellow of the AAS last year as well. He's also won awards from Canada, the Beals, the Rutherford Memorial Medal. He's a Fellow of the Royal Society of Canada and also of the Society of London, and he's a member of the National Academy of Sciences. If you look on the internet, you'll find out that Scott is a climber. I Googled Scott Tremaine climber, and what came up was an Alpine Club article written by David Schramm back in 1981 that lists their climb on Chimborazo in Ecuador. And it's described as a steep slope with rotten rock. So I hope the climbs he's doing now are a little bit safer so that he can continue all his work on dynamics, the excellent work that he's doing. So today his talk will be on comets, unseen planets, and the outer fringes of the solar system. So welcome, Scott.
Thank you, Paula. It's a real pleasure and an honor to be speaking at the National Astronomy Meeting, and particularly so to share the sort of reciprocal arrangements with Sandy Faber, who's a longtime collaborator and friend. The subject of the talk is comets in general. I'm going to spend the first half of the talk talking about what I call the standard model for the formation and evolution of comets. And then I'll move on to the more specific topic of what comets can tell us about hypothetical planet X in the solar system. For the purposes of this talk, comets are basically chunks of ice and rock, a few kilometers in size. They're probably rubble piles, as indicated by their very low density, less than a gram per cc. Typical masses are a few times 10 to the 16 grams. They're believed to be leftover small bodies. I'll use the term planetesimals and comets interchangeably, leftover small bodies from the assembly of the planets. Of course, the reason that comets are so spectacular is that they develop an atmosphere or coma and a tail when they approach the sun. Comets actually have two tails. It's most clearly illustrated in this picture. There's a dust tail whose dynamics is determined by the radiation pressure and solar gravity, and there's a plasma tail that's entrained in the solar wind. Because of these, the tails only develop when comets are close to the sun. At large distances, comets are visible only by reflected light from the solid body, from the nucleus of the comet. And that means that their brightness falls off like 1/4 power of the distance from the sun, 2 powers for the light to get out there and 2 powers for it to get back. The consequence of that is that very few comets are discovered at distances beyond a few astronomical units, although the Rubin Observatory is going to do much better in the next few years. The other consequence is that because so much material is emitted in the tail, once a comet becomes visible, it can't survive for more than a few hundred orbits. Since the orbital periods are much less than the age of the solar system, the kind of inevitable consequence of this is there has to be some sort of reservoir for the comets. And the reservoir has to have two properties that are in tension. It has to be sufficiently stable to store comets for timescales of order gigayears, but on the other hand, it has to be sufficiently leaky to produce a constant flux of new comets that are the comets that we see. And trying to determine the properties of these reservoirs, where they are and how they behave, is one of the main themes of the study of the origin of comets. In order to talk about this, I'll be using orbital mechanics, so I'm just going to review the kind of first year results on Kepler orbits. They're characterized by a semi-major axis and an eccentricity. The perihelion, the point of closest approach to the sun, is the semi-major axis times 1 minus the eccentricity. The inclination I'm always going to measure relative to the ecliptic, to the plane of the planets. The orbital period is related to the semi-major axis by Kepler's law, which says that the square of the period in years is equal to the semi-major axis in astronomical units. The energy per unit mass is g times the mass of the sun divided by twice the semi-major axis. It's conventional to simplify this in comet studies by setting g to 1, the solar mass to 1, 2 to 1, and minus 1 to 1. So we just treat 1 over the semi-major axis as a proxy for the energy. And just as a reminder, Neptune's semi-major axis is 30 astronomical units, and the nearest star is about 270,000 astronomical units from us. This is a plot of the known comets, inclination on the vertical axis, orbital period on the horizontal axis. A lot of comets have orbits that are very nearly parabolic. That implies very long periods, so I've simply plotted all of the comets with extremely long periods at a period of 10 to the fifth years. The really striking feature of this plot is that the comets are cleanly divided into two groups. There's a group with orbital periods less than about 20 years and inclinations less than about 30 degrees, and a group with a roughly isotropic distribution of inclinations and a wide range of orbital periods longer than about 20 years. Looking first at the short period comets, it's pretty clear from the fact that these are flat that they have to come from a flat source. That is, that the reservoir for the short period comets has to be a flattened distribution like a disk. The reason for that is simply that you can't have any kind of gravitational interaction bouncing around between the planets that's going to take a spherical distribution and convert it into a flat one. So the short period comets have to come from a flat disk aligned with the planetary system. This was already recognized in the 1980s, And then in the early 1990s, Jewett and Liu discovered the first example of a population of comets beyond Pluto that's now known as the Kuiper Belt. There are now several thousand objects known in the Kuiper Belt. The Rubin Observatory is expected to discover about another 100,000. And it's believed that the Kuiper Belt is the reservoir for most of the short period comets in this group. It's located in a region about here. Most of the orbits in this region are relatively stable, but occasionally one of the orbits gets perturbed onto a Neptune crossing orbit and then bounces back and forth between the planets and random walks down into the region where it becomes detectable as a short period comet. The leakage from the Kuiper Belt is probably not fully understood, but is probably some combination of collisions between bodies, non-gravitational forces, and weak orbital instabilities. I'm going to spend more time talking about the origin of the distribution of spherically distributed or isotropic comet population with periods longer than about 20 years. In order to explore this distribution, rather than using the orbital period, it's better to use the energy, 1 over the semi-major axis. That's the first modification. The second modification is to recognize that all of the orbital periods that we're seeing here are the orbital periods that the comets have after they've passed under the influence of the giant planets, after they've passed by Saturn and Jupiter. And that means that the orbital period that they have is not exactly the same orbital period that they had when they entered the solar system. The typical kick that a comet gets in passing from outside the solar system to where we can see it is about 10 to the minus 3 in inverse astronomical units. So it's better to plot the original energy, that is simply to numerically extrapolate the orbits of the comets back outside the planetary system until they're out at semi-major, out at radii of 50 or 100 astronomical units, and figure out what the semi-major axis was back then. When you make those changes, you get a plot that looks like this. Again, it's a plot of the inverse semi-major axis when the comet was outside the solar system. What you can see from this is that 0 corresponds to a parabolic orbit. Orbits with negative inverse semi-major axis are hyperbolic and therefore correspond to unbound comets. So you can see in this that there's a few unbound comets, but all of these have been subject to non-gravitational forces, have larger observational errors than usual, or some other reason that the orbit's not entirely trustworthy. And I think it's fair to say that there's no well-defined case in this region of a comet coming into the solar system with a hyperbolic orbit. There is, of course, Comet Borisov, which was discovered just last year, but it's coming in from a really hyperbolic orbit in these units. It's about 10 to the 5th or minus 10 to the 5 or minus 10 to the 6 astronomical units. So the existence of this large peak in a region between about 10,000 astronomical units and parabolic orbits with a peak at about 30,000 astronomical units says that the reservoir for the long period comets has to be located at around 30,000 astronomical units. That's a remarkably large distance. It's 10% of the distance to Proxima Centauri. Nevertheless, I think the evidence from this is strong enough that there's no doubt that this is the reservoir for the long period comets. The person who first recognized this clearly was Jan Oort in 1950, and this has come to be called the Oort cloud. Let me just stress again for a minute how remarkable this is. And one way to think about this is to imagine a modification to gravity in which the standard gravitational potential was modified by a Yukawa term, an exponential cutoff in the gravitational potential. If the potential is Newtonian, escape energy, of course, is at 0. As you increase this parameter m, which is an inverse distance or a mass in elementary particle physics units, the escape speed moves inward. If, for example, the mass parameter is the inverse of 40,000 astronomical units, which corresponds to about 3 × 10⁻23 electron volts, the escape energy would move so that it excluded most of the Oort cloud. So the existence of the Oort cloud sets a secure limit on the mass that goes into the Yukawa potential, essentially the mass of the graviton. And just for comparison, this limit is actually better than the limit that came from LIGO's observation of simultaneous gravitational waves and photons from the binary neutron star merger. The other comment I'd like to make on this is that if you go back to Oort's original paper, this is the data that it was based on. Instead of the hundreds of comets in the peak that we have now, he had roughly a dozen. And I think the moral from this is that in these days where we hear a lot about big data, small data is sometimes sufficient if you have a clean system and if you're as smart as Oort was. The next thing to think about is the comets that aren't in the Oort cloud that are in this distribution in here. And the explanation for that's quite natural. I said that in the process of passing through the planetary system, the typical comet experienced a kick of about 10⁻³ inverse astronomical units. That means after a comet comes into the planetary system the first time with nearly zero energy, it'll come back either with a positive energy, in which case it escapes, or a negative energy, in which case it'll appear somewhere in this distribution here. And every subsequent passage, it will continue to undergo a random walk in energy. It's essentially the classical gambler's ruin problem, which tells you that the fraction that survive for n orbits after entering the solar system the first time goes like n to the -1/2. In order to fit this accurately, you need to also assume some sort of fading law. This is a natural physical consequence of the fact that the inventory of volatiles near the surface of the comet gets depleted every time it comes close to the sun. And for plausible fading laws, you can reproduce this distribution quite well. You can do more with the dynamics of the Oort cloud. Comets of the Oort cloud are sufficiently far from the sun that they're subject to gravitational kicks from passing stars and torques from the galactic tide, and those are sufficient to randomize the orbits in the cloud over a time less than the age of the solar system. That means that the distribution of energies and the constant distribution of comets and the constant energy surface in phase space is approximately uniform. It's essentially equivalent to a microcanonical ensemble from statistical mechanics. If you work through what the consequence of that is for the distribution of perihelia, it turns out that the fraction of comets with a given semi-major axis that have a perihelion less than some value q is just linear in q. It also implies that the comet's distribution is isotropic, that is, the fraction with inclination less than cosine of some value is uniform in the cos of the inclination. If you actually look at the distribution of comets that are observed coming from near the Oort cloud, those conditions are satisfied. The distribution in perihelion distance is almost exactly linear in perihelion distance until you come out to large perihelion distances where you start to lose comets from observational selection. And similarly, the distribution of inclinations is uniform in the cosine. You can do still more because you can use these results to estimate the total population of comets in the Oort cloud. We get roughly one new comet per year arriving from the Oort cloud with a perihelion of less than 1 astronomical unit. We know the orbital period at 30,000 astronomical units is about 5 megayears. We know that the fraction of comets with perihelion less than q is 2q/a. So and we know that they're uniformly distributed in q. That says that the number of comets in the cloud is just the rate they come by through 1 astronomical unit times the orbital period times the inverse of this fraction. And if you plug in the numbers I've given so far, you get a population of about 1 × 10⁻11. With a typical comet mass I estimated before, that says the total Oort cloud mass is around an Earth mass. I'd also like to give another shout out to Oort. This is a number that was first estimated by him. It was an extrapolation of a factor of 10 to the 10th from the data that he had, but we still believe that number is correct within a factor of a few. You can say still more about the dynamics of the Oort cloud, and to do that, I want to diverge for a second to talk about the behavior of stars and nuclear star clusters close to supermassive black holes. A typical supermassive black hole in the center of a galaxy is surrounded by a star cluster. If stars come too close to the black hole, they get tidally disrupted or swallowed by the black hole. That says that if you have a star with some, and you look at its distribution of velocities, there's some cone or range of velocities that are so close to radial that it means that the star will come so close to the black hole that it'll be tidally disrupted or eaten by the black hole. The star's encounters with other passing stars in the nuclear star cluster lead to a random walk in velocities. And so velocities that are out here can random walk into the loss cone, at which point the star is disrupted, giving rise to a tidal disruption event. Exactly the same process applies to comets. All I'm going to do is replace the supermassive black hole by the sun, replace the cluster of stars by the Oort cloud. And in this case, if the non-radial component of the velocity is too small, the comet enters the loss cone. In this case, the loss cone is the range of perihelia that's sufficiently small, typically about 15 astronomical units, that the encounters with the giant planets, Saturn and Jupiter mainly, give it a kick in semi-major axis that's large enough to remove it from the Oort cloud. So I've just replaced tidally disrupted by the black hole with the energy kick being large enough to eliminate the comet either into an escape orbit or into a much more tightly bound orbit. So if you imagine sitting on the star and looking in towards the sun, you'd see something like this. You'd see the loss cone with a corresponding to a perihelion distance of about 15 astronomical units. And for a typical relatively small comet, there'd also be a range of perihelion distances at which it could be detected, which here I've, as an example, given as 2 astronomical units. Then you can see that there are 2 cases for how this random walk in the stellar velocities would work. If the step in velocity per orbit is much smaller than the distance across the loss cone, it would simply random walk outside the loss cone, get a little bit inside the edge of the loss cone, and then be lost. In that case, we'd never see it because the comet never gets close enough to us to become visible. The only time in which the comets are visible is if the change in velocity that the comet receives during a typical orbit is sufficiently large to take it from outside the loss cone to inside 2 perihelion distance of 2 astronomical units in less than 1 orbit. So the only reason that we see the comets in the Oort cloud, the only reason we're aware of the Oort cloud's existence at all is because this kick is large enough to take us from well outside the loss cone to radii small enough that the comets are visible. That kick in perihelion is a strong function of semi-major axis. In fact, it goes like the 7/2 power of the semi-major axis. So that tells us that this case, the case where the loss cone is full, is only true if the comet has a sufficiently large semi-major axis. Knowing the properties of the stars in the solar neighborhood, you can work out how large that semi-major axis has to be. It turns out to be about 35,000 astronomical units. You'll notice that this is exactly the size of the peak in the distribution of semi-major axes in the Oort cloud. The conclusion is that we can predict the size of the Oort cloud with no free parameters. The other consequences of the Oort cloud might extend to much smaller radii and have far more comets than we think it does. Okay, so far I haven't said anything about the formation of the Oort cloud, but in fact it's pretty straightforward to come up with a compelling standard model of how the cloud was formed. You start with a simple set of assumptions. You assume that the giant planets are fully formed and either in their current orbits or in orbits that have migrated by an amount you estimate from theories of formation of the solar system. Then you sprinkle leftover test particles or planetesimals on nearly circular coplanar orbits between the planets and outside the orbits. You assume the galactic environment is the same as it is now. Then the gravitational perturbations from the giant planets gradually excite the eccentricities of the comets until their orbits cross the planets. Then they have continued interactions with the planets that cause their orbits to random walk either to larger or smaller semi-major axes. And eventually, when the semi-major axes are large enough, gravitational kicks from passing stars, the torque from the galactic tide add enough angular momentum to the orbits so the perihelion grows. They no longer come close to the planets, and the evolution in semi-major axis is frozen out. In other words, the comets have joined the Oort cloud. The eccentricity of the orbit, the orientation of the orbit continue to change, but the evolution in the semi-major axis becomes much slower. And the wonderful thing about this standard model is that all of its properties can be worked out simply by doing large, long n-body integrations for the giant planets, a large number of test particles, and passing stars in the galactic tide. This is an example of one of these calculations from Dones et al. About 15 years ago. This is the population of the outer Oort cloud over 5 gigayears. It grows and peaks at when the solar system was about a gigayear old and is now declining. This is the population of the outer Oort cloud, semi-major axes, bigger than 20,000 AU, corresponding roughly to the range that we can see. This is the invisible inner Oort cloud. You can see that in this model, it's about the same total population as the outer Oort cloud. And these are the comets that are in transit, that still have perihelion inside the giant planets and are gradually random walking their way out to the outer Oort cloud. The efficiency of putting planetesimals into the outer cloud is about 2 or 3%. If you put in standard estimates of the amount of planetesimals that are left over after formation of the giant planets, and put in this efficiency factor of 2.5%, you get a mass of the outer Oort cloud, which is about 1 Earth mass, which you remember is the mass that Oort estimated 50 years ago on the basis of an extrapolation of a factor of 10 to the 10th. This is a more recent simulation which shows similar results. Here you can see that the eccentricity of the surviving comets is increasing with the semi-major axis. That's simply because these are the comets that are in transit. They still have perihelion distances, perihelia that cross the giant planets. So the eccentricity is increasing with the semi-major axis. You can see that the inner edge of the Oort cloud is around a couple of thousand astronomical units. It reaches out to over 100,000 astronomical units. And it's roughly spherical. This is the inclination distribution out past about 5,000 astronomical units. These simulations also predict the distribution of comets in the inner Oort cloud. And here you can see again what you would expect, that in order to see comets with semi-major axes less than about 20,000 astronomical units, you have to go out to perihelion distances of 15 to 20 astronomical units. This population of comets is currently completely invisible to us. We understand the population out beyond about 20,000 AU, but whether this model is correct, that is whether models based on the formation and standard model are correct, is something we'll only be able to tell when we can get a significant population of comets with these perihelion distances, and the hope is that that's going to be possible with the Rubin Observatory. I've talked about the standard model. It's similar to the standard model of particle physics. That is, it explains a lot of the observations, but not all of them. And it certainly leaves out some physics that's poorly understood. The sun probably formed an dense star cluster with different tidal fields and stellar perturbations. Planetary orbits have migrated by unknown amounts. The sun probably migrated the galactic disk by an unknown amount. And other massive bodies might have been present in the protoplanetary disk. Rather than review all of these issues, I'm going to focus in the last part of the talk on this particular concern. Okay, so the story of comets and Planet X really begins with the discovery of Sedna by Brown et al. In 2003. Sedna has about 500 kilometers radius. It has an aphelion of almost 1,000 astronomical units and a perihelion of 75 astronomical units. Perihelion is so large that its orbit is not influenced by any of the planets. That is, if you integrate its current orbit forward for 5 billion years or back for 5 billion years, it basically stays the same. Sedna is not the only object like this. There's something like 30 other examples known by this, and this population has come to be called the detached disk. It's detached because it doesn't interact with any of the giant planets. Now, in the standard model, all planetesimals form in nearly circular, nearly coplanar orbits in the protoplanetary disk. And there's no way to create Sedna in the standard model. So the question is, how did Sedna and how did the other members of the detached disks get into their current orbits? And I'd like to argue that the resolution of this apparent paradox is the standard model is oversimplified. It contains two populations. It has the giant planets and it has a population of test particles. But in fact, the planet formation process is likely to produce solid bodies with a continuous distribution of masses. After all, Jupiter, Saturn, Uranus, and Neptune have solid core masses of roughly 10 Earth masses. That suggests that at least a few Earth mass bodies and probably many more Mars mass bodies of a fraction of an Earth mass were likely to be present in the protoplanetary disk. Because they have masses much smaller than the masses of the giant planets, they'll still be scattered in random walk towards the Oort cloud along with the comets, but they can have a dramatic effect on the comets. The reason is that most of the evolution from semi-major axes of a few tens of astronomical units out to tens of thousands of astronomical units occurs at nearly constant perihelion distance, because the only kicks they're getting are from the giant planets at small perihelion distances. On the other hand, if you have a massive body that's in an extended orbit, it's much more efficient at exerting a torque on the comet. So for example, if you have an Earth mass planet with a semi-major axis of a couple of hundred astronomical units and a comet with a similar semi-major axis, the planet can exert enough torque on the comet during the time while it's spending at this size to expand the perihelion distance well outside Neptune's orbit, and then freeze it in place. That is, freeze it in place in an eccentric orbit with a semi-major axis of a few hundred to 1,000 astronomical units. It can, in other words, it can raise the perihelion distance large enough to create orbits like that of Sedna. Once again, you can simulate this. These are simulations done by Kedron Silsby as part of his PhD thesis with 4 giant planets plus a few dozen extra bodies of masses around an Earth mass plus a large number of test particles. These are the distribution of the surviving Earth mass bodies after 4.5 billion years. You can see there's a distribution of perihelia out to about 100 astronomical units, and a distribution of semi-major axes out to about 500 astronomical units, and a distribution of inclinations out to about 30 or 40 degrees. What this says is that you're naturally and automatically producing a detached disk with many of the right properties. This is a plot of the actual distribution of bodies in the detached disk. You can see the inclination distribution is roughly correct. You don't reproduce this large bundle here, but this is low eccentricity bodies that are probably part of the primordial Kuiper belt. And you produce a distribution of perihelion distances that's about right. The observations are biased towards smaller perihelion distance simply because those are easier to discover. Not only do you automatically produce a detached disk with about the right properties, but in about half the simulations, 1 or 2 extra bodies of masses between Mars mass and Earth mass survive with semi-major axes less than about 250 astronomical units and perihelia around 50 astronomical units. The conclusion is that it's likely, although not certain, that the solar system contains an undiscovered planet of mass, say, between Earth mass and Mars mass, with a semi-major axis distribution less than a few hundred astronomical units. So let me just review the evidence for and against Planet X of this kind. To do that, I have to give you a bit of a scorecard on Planet X. It was originally proposed as a body that caused unexplained anomalies in the orbits of Uranus and Neptune. Those arguments led to the discovery of Pluto, but Pluto's mass is too small by more than a factor of 1,000 to produce the anomalies that were claimed. It's now generally recognized that the anomalies arose because the mass of Neptune was misestimated by about 0.5%. So that Planet X has gone away. A more recent proposal is that Planet X is a body that creates asymmetries in the distribution of the directions of distant Kuiper belt objects. This is a Caltech proposal from Batygin and Brown. And the motivation for that proposal is that the semi-major axes, the major axis orientations of Kuiper belt objects exhibit unexpected correlations in 2 of their orbital elements. Physically, that implies that the distribution of long axes of the orbits is not axisymmetrically distributed in azimuth around the solar system. You can see here that there's a modest but significant bias in one direction. And Batygin and Brown have argued that this concentration is due to the dynamical effects of a distant planet of around 5 to 10 Earth masses at about 500 astronomical units. There are some possible concerns with this hypothesis. It's always possible that the clustering is a statistical artifact. There are only really, in the sample that they used to establish this, there were only 14 objects. There are arguments going back and forth that the clustering could be due to observational bias. And finally, a planet with this large mass and these orbital properties is pretty hard to form again in the required, in any sort of model for the formation of the solar system. And so the question of the origin of this Planet X has been left unresolved. It could be that there's a Planet X that's been ejected into the Oort cloud along with the comets. That would give it a semi-major axis of around 10,000 astronomical units. If it's Earth mass, a body out there would be essentially impossible to discover. Or it could be, as I've suggested already in this talk, that it's a massive body that created the detached disk and is surviving in the same region as the detached disk, out at distances of a few hundred astronomical units. The observational constraints on Planet X I'll go over rather quickly. In the extreme case where Planet X is large enough to be a giant planet like Jupiter or Saturn, it's self-luminous in the infrared. And so all-sky surveys like WISE produce pretty strong limits on any such planet. WISE has ruled out any Jupiter analog within 80,000 astronomical units or a Saturn analog within 30,000. Terrestrial planets are much harder because they're mostly visible by reflected light, so the flux falls off much more quickly. There are a variety of recent surveys. The Rubin Observatory will produce a deeper survey, but even that will not have all-sky coverage or even complete coverage of the ecliptic. One of the more interesting possibilities is that future surveys of the cosmic microwave background can offer strong constraints on the existence of a planet, simply because even though terrestrial planets are mostly visible in reflected light, once you go to sufficiently long wavelength, they can be self-luminous. There are dynamical constraints from the traditional method of fitting to solar system ephemerides, from pulsar timing, and perhaps the most interesting from gravitational lensing of stars in the Gaia catalog. This will require the final data release from Gaia to be investigated, but I think this is perhaps the most interesting and unusual way of detecting Planet X. All right, let me just briefly summarize. We have a simple standard model for the formation of the Oort cloud. It explains most properties of observed comet orbits, but not all of them. One of the major shortcomings of the standard model is explaining the formation of sedna and other members of the detached disk. But these could be explained by the presence of terrestrial mass bodies in the protoplanetary disk. And there's a significant possibility that one or two of these bodies are still in orbit, not that far away from the sun. In the next decade, there'll be a variety of new and improved probes looking for Planet X. Obviously, if you don't find it, you can't rule it out, but if you do find it, it'll be incredibly interesting. And perhaps while I'm answering questions, I'll put on a final slide that is a summary of the current observational constraints on Planet X. Thank you.
All right, thank you, Scott. That was a very interesting talk. You covered a lot of different areas. We have one question that's come in from David Kinson. It says, thanks for the very interesting talk. Could the effects of Planet X be accounted for by multiple smaller bodies, several Sedna-like or more smaller asteroid-like bodies?
In principle, excuse me, in principle, it's possible, but I think it's unlikely. These bodies are likely to be ejected in random directions, and so any torque that they exert on the comets is likely to cancel out. So I think your best bet is bodies between Mars mass and Earth mass. It's possible you could get away with something smaller than that.
Okay, another question. How will the Rubin telescope discriminate asteroids from comets at 20 AU?
Well, the simplest answer is that if it's a 20 AU, you wouldn't define it to be an asteroid. But if the question is how will it discriminate asteroids from general bodies at 20 AU, the apparent angular speed of the asteroids is going to be much larger because they're much closer. And in fact, when the object's at 20 AU, the proper motion, either the reflex motion due to the solar motion or the intrinsic proper motion, is usually sufficient so that you can get a pretty good first estimate of what the perihelion distance is, what the current distance is.
Okay, next one by Kathy Romer. Any reason why there can't be a planet Y, Z, etc. too? The simulations seem to favor several at greater than mass of the Earth.
Yes, that's in the simulations we did. We got one or two simulations with two planets, and most of them had one surviving. So that's the only reason for thinking that there's only a Planet X and maybe a Planet Y. But obviously, I'd be happy enough if there were more than two.
Okay, from Rudiger Voss, how are the chances, in your view, of that Planet X is not a planet at all, but a tiny black hole?
Well, so certainly there has been a lot of discussion in the literature, or at least some discussion in the literature, that since that the Planet X is really a black hole, I think of that as relatively unlikely. That is, the original motivation for thinking that Planet X might be a black hole is that the searches for Planet X haven't discovered anything yet. But I think the theoretical arguments for a Planet X are not so compelling that we should jump to the conclusion that it has to be a black hole. If you continue to look for Planet X and you can't find it, I think the most likely explanation is that it's not there, rather than that it's there and it's a black hole.
Okay, Tanmoy Lasker, how do constraints on the gravitational non-Newtonian Yukawa potential scale length change if you include the uncertainties on the semi-major axes of the Oort comets in the calculation?
They don't change very much. There are some comets there's a range of quality of the comet orbits, and if you restrict the comet orbits to the ones that are best determined, you get the same semi-major axis distribution for the Oort cloud. So although some of the orbits have big uncertainties, either because the observations aren't that good or because of non-gravitational forces, there are enough with high quality observations that I think that doesn't change the argument.
Okay, something flashed up from Keith Horn, but it doesn't appear in the chat. Let's see, is that still coming over, Patricia? Oh, here it is. Okay. Can we use, this is from Keith Horn, can we usefully probe KBO and or Oort cloud by placing high-speed CMOS cameras in the focal planets on the outskirts of the field of many large telescopes, must be focal planes, to look for short occultations of random stars?
In principle, that can be done. There is a survey called TAOS-2 that's being run out of Taiwan to use a telescope, I think in Baja, California, to look specifically for occultations of stars by comets in the Kuiper Belt. There's also been a proposal for a space mission called Whipple, which would carry that to an extreme, and the designers of Whipple claim that they could actually detect occultations by comets in the Oort cloud and the Kuiper Belt. I don't think there have been any I don't think there have been any conclusive results that really put additional constraints on the properties of the Kuiper Belt from TAOS yet. There was also a detection of a couple of occultations from the Hubble telescope fine guidance sensors, and those have been used to attempt to constrain the distribution of sizes in the Kuiper Belt. So I haven't heard about or thought about the possibility of putting extra detectors on existing telescopes, but that would be very interesting to look at.
Next question is, would a lump of dark matter be a possible candidate?
It would be unlikely for any, well, it's certainly possible, but I think it's unlikely. It's difficult to find a mechanism in which standard models of dark matter, in standard models of dark matter, it's difficult to find a mechanism to capture any significant amount of dark matter by the solar system. It would require some sort of unconventional form of dark matter. If you're going to have a lump of it, it probably has to be baryonic, and baryonic dark matter is disfavored from cosmic microwave background and nucleosynthesis arguments. So I'd say it's possible, but it would require a pretty radical revision in the standard models for dark matter.
Yeah, question from Chloe Sumner. Is the general structure of the Oort cloud stable over time? So is the rate of new comets constant, presuming no external disturbance?
Almost certainly no. So there are two effects. There's a gradual decrease in the amount of material in the Oort cloud. I showed in one of the slides that it's already a factor of a few smaller in total population than it was at its peak when the solar system was about a giga-year old. But on a shorter time scale, individual stars happen to come close enough to strongly perturb the Oort cloud, can sort of shake the tree enough to dramatically change the flux of new comets coming in over million-year timescales. So the way to think of it is not really as a steady stream of new comets, but as something that's undergoing peaks and troughs and sort of like, rainfall is a function of time. The degree in which it varies on million-year timescales depends on the total amount of mass in the inner cloud, because it's more strongly affected by this. But you're right that there is likely to be a significant amount of temporal variation in the number of comets coming in from the Oort cloud.
Okay, I don't see another question. Let's see. Okay, following on from the dark matter hypothesis, what would you personally think would be more exciting, a planet, DM, or a black hole?
Well, it's a good question. I think a black hole would be more exciting. The only downside of a black hole is it's going to be a lot harder to investigate. If you have a planet there, the nice thing about a planet is once you find it, it's relatively easy to observe. And the only question is looking for, how to find the needle in the haystack. With a black hole, even once you knew it was there, you'd have a hard time finding it. You'd have a hard time doing much exploration of it. And the really exciting thing about one of the techniques, about the techniques I mentioned, in particular, looking with next generation cosmic microwave background surveys, or looking from the gravitational lensing effects on the Gaia catalog, is that you have a potential to really localize the location well enough that it should be straightforward to find it and confirm it if it's a planet. If it's a black hole, then you might have a problem.
Okay, I think that's it for the questions for now. I actually have one. You referred to this interstellar comet thing that happened about a year ago. Was that, do you consider that a once in a lifetime event, or are we just detecting with our better detectors now that we can expect to see more of these?
Well, I want to stress that the comet Borisov was discovered by an amateur. And so I think what it really tells you is that the quality of the research that's being done by amateurs in this subject has grown sufficiently rapidly that it's impressive that that they were the ones to discover this rather than any of the professional surveys. Having said that, obviously I can't tell whether it's a once in a lifetime event or not, but my guess would be that it's simply reflecting the fact that the capabilities of both amateurs and professionals to discover comets have been increasing pretty rapidly over the last several decades. And we've just intersected the point where we're going to be discovering these things at fairly regular intervals from now on. And that'll be great, because it's very hard to, we've discovered two. There was a Oumuamua and Borisov. The two of them are completely different. And we just need a lot better statistics to figure out what they're telling us.
All right. Well, thank you for a wonderful talk, and congratulations on the Russell Prize. And we'll close the session, but I think Patricia has there's be a few closing statements. If you want to do those now.
Yeah, sorry, pressing the wrong buttons there. Thank you very much, Scott and Paula, for a great final plenary talk to this NAM conference. And I did just want to use up a few minutes of this plenary slot just to thank you, to kind of give a few thanks to everybody that's helped out in putting this together. So I'm going to distract you, sorry. I'm sure that I hope you won't mind, you'll indulge me for just a couple of minutes to take up some time just to thank the LOC for their hard work during these past few months in putting this together, this virtual conference. Specifically, I did want to name some names, so sorry, but Dave Tsang and Tanmoy Laskar, thank you for your fantastic and tireless work on the poster session, and much, much more. Then also Bethan Eastman for keeping you all informed through the tweeting of events and activities taking place this week, and for her last minute help and support, for example, getting Slack set up for you all to carry on your conversations, post sessions and plenary talks. Vicky Scowcroft, Stan Wurtz and Hendrik van Eerten for setting up the virtual platform, as well as all the other long, extensive list of LOC activities during the last few months. And then finally, I'm sure that you'll all agree that the support provided by our ambassadors to resolve technical issues has been outstanding during the sessions. But of course, it's important to note that the meeting couldn't take place without the hard work from the session conveners and chairs as well, and the excellent talks and posters that we've heard and seen. And of course, the wonderful and diverse range of plenary talks. So again, thank you all, and thank you, Professor Scott Tremaine, for ending this week with such a great, interesting and informative plenary. It's been wonderful, and it's been a real privilege to be able to sit in on all these talks. Then for all of you that missed the announcement, we now happily, the University of Bath now happily hand over the baton to the University of Warwick, who will be hosting NAM 2022. And so we wish them a highly successful meeting, and we hope that there will be more in-person activities and experiences that we were unable to offer at this NAM. Nevertheless, we're of course very happy that it was able to take place. Last and not least, we are very interested in getting your feedback. And so you will be receiving an email early next week with some post-NAM relevant information about plenary recordings, for example, as well as a request to complete an online feedback form, which we'd be very keen for you to complete as best to your ability. So thank you very much, and enjoy the last block of the sessions, and have a great weekend.